So now let's understand what are the different possibilities when we are given with a geometry which is a plane wall geometry. So there are three main cases. Either we have plane wall, either we have cylindrical geometry, or either we have spherical geometry. So in this one we'll look at the different possibilities of boundary conditions which we have seen recently. So the various boundary conditions which I have explained were this: the constant surface temperature, constant surface heat flux, adiabatic, convection, radiation, interface boundary condition, and thermal symmetry. So there could be multiple possibilities and combinations of this with a plane wall. So let's look at some of the possibilities. So first we are given with a plane wall which is 1D, steady state, there is no heat generation, so Qgen is 0. So these are the simplicities we are given. So with a plane wall which has a conductivity K, temperature T1 is on the left side, T2 is the surface temperature on the right side, and assuming T2 is less than T1, we are assuming this. So with this given condition, my heat equation becomes d2 square by dx square, second order differential of temperature with x is equal to 0. How did we receive this equation? You can go back to another video where I have been explaining the simplifications for a heat diffusion equation. So this was the fifth level of simplification, and you can go back to that video and look and get more clarification. So with this, let the boundary conditions be given as at x equal to 0 we are given as t is equal to t1, at x equal to L we are given as t is equal to t2. This is the thickness L, and let's use one of the boundary condition first. So d2 square by dx square is equal to 0 means integrating this we get dt by dx is equal to some constant c1, and again if we integrate this, what we get is t is equal to c1 into x plus c2. So this is our equation. Now using one of first boundary condition, t at x equal to 0 is given as t1. That means my t1 is equal to, I'll put x equal to 0 in this equation now, c1 into 0 plus c2, that means c2 is equal to t1. Now we'll use the second boundary condition, that means t at x equal to L is equal to t2. This will be used, and this means my t2 is equal to c1. I'll put x equal to L in this condition, and t will be t2 now, c2. That means c1 into L plus c2 is already known as t1. That means my c1 value, rearranging this equation as t2 minus t1 upon L. So this is my value of c1, this is my value of c2. I can put these values back into the original equation. Hence my temperature is equal to T2 minus T1 upon L into x plus T1. Now I can put the values of x from 0 to L and get the value of T at any given location x. Okay, so this is called as Tx. Now I can rearrange this and get T1 minus T minus T1 is equal to T2 minus T1 into x by L, and using Fourier's law, let's use Fourier's law. My q dot is known as Ka dt by dx, and now I'll use this temperature representation T of x, differentiate it and put it in this q dot expression. So what does that include is, since this is a constant, this will get this will be equal to 0 when I differentiate, and when I differentiate this term, my x will go to 0 and the coefficient remains as it is. Hence my dt by dx is simply t2 minus t1 upon L. And when I rearrange this term, this equation, using this x and these two things, what I have is q dot is equal to t1 minus t2 upon L upon Ka. Why did I write it in this specific form? That is very important to understand, and that will be helpful when we solve problems. So now I am taking t1 minus t2 as a potential difference, potential, and L upon Ka is my resistance. Or if I do not want to use L, I can write some length dx upon Ka is my resistance, thermal conduction resistance, RTH for conduction. That is conduction coming because I am having K over here. And when we use convection, we will have some other expression, but this resistance value of L by Ka is very important. And I have given that analogy also, that this is the potential, this is the resistance, hence potential divided by resistance give me the effect. The effect is the heat transfer. So when I represent this in a form, an electrical circuit form, that will be something like this. At this location I have temperature T1, at this location I have temperature T2. This is the resistance RTH, whose value is L by Ka, and what is moving is Q dot. What is moving is Q dot. So this is an analogy that I have voltage V1, I have voltage V2, there is a voltage drop of V1 minus V2 across this resistance whose value is L by K, and my current flowing is analogous to my heat transfer or heat which is flowing. Okay, so this was the first boundary condition or first possibility with the plane wall. The second possibility which would be there is a convection. So over here there was nothing which we could we assumed that there is no fluid moving, there is nothing, but over here we assume with fluid motion. Over the wall. So what we have is something like this: K T of x. Still we are assuming steady state. This is temperature T1, surface temperature T2. Over here the fluid is moving, over here the fluid is moving with H1 and T infinity 1, with H2 and T infinity 2. These are the properties, the upstream temperature and convectivity, upstream temperature and convectivity of the second fluid. Okay. Now we are assuming what all the things which were in the earlier case, 1D, steady state, and heat generation is 0. So now we can directly write everything in terms of the resistance. So what we have here is like this. Over here we have T infinity 1 temperature, then some heat transfer is occurring and it is reaching some temperature T1, which is this surface temperature. Then there is some conduction happening and we are reaching this surface which is at temperature T2, and again there is some heat transfer occurring to the fluid which is at temperature T infinity 2. Assuming T infinity 1 is greater than T1, which is greater than T2, and which is greater than T infinity 2. This is an assumption. The direction of heat transfer can be anything, we doesn't focus on that. But so we'll see what is the equivalent resistance of the conduction. So when we are looking at a conduction problem, the equivalent resistance is 1 by HA. This is the resistance for the convection case. We have already known for the conduction case the resistance is L by Ka. Now let's look at the units. So over here we know that the unit for resistance conduction or the units for resistance should be equal every time. So taking this L by Ka into account first, the L has the units of meter, K has the units of watt upon meter Kelvin, and area has the units of meter square. Hence this meter and meter cancel, this meter and meter gets cancelled. Hence the unit of resistance becomes K by W. Again this resistance over here, so H is the convectivity and it has the units of watts per meter square Kelvin. Hence my units become 1 upon watts per meter square Kelvin into the units of meter area, which is meter square in the denominator. This gets cancelled. Hence my unit of thermal resistance for convection is Kelvin upon watts. Okay, fine. Hence let's write equivalent resistance is over here. So my resistance for this will be convection. This is the heat transfer between the fluid and the surface is convection. Hence my resistance will be this much. Over here for conduction we have already known the resistance is L by Ka. Hence this is L by Ka. And for this again there is convection between temperature T2 and between the fluid. Hence this will be H2A. Now we'll write the net resistance which are in series. Net resistance in series will be RTH net. That will be the addition of all. So it will be H1A plus L by Ka plus 1 by H2A. Now I can write the Q dot, net Q dot. So Q dot we already know is delta T, which is the potential upon the resistance RTH net. And now this will be T infinity 1. Over here the delta T is the complete delta T, because the resistance is net. That's why the temperatures are also net. That is the first temperature and the last temperature. Okay, so this is the expression for Q dot. And we can also write separate expressions, because my Q dot will also be equal to T infinity 1 minus T1 upon 1 by H1A. This will be equal to T1 minus T2 upon L by Ka is equal to T2 minus T infinity 2 upon 1 by H2A. These threes are also equal because the same heat is moving from this end to this end to this end. Everywhere the same heat is flowing or same heat flux is moving. Hence these three heat are equal. So this expression can be used at so many locations to find out if we are unknown with some temperature, or if we are unknown with H or H2 or L, K, anything. So a combination of coefficients and things can be given, and a combination of things can be asked from you. Now we can go to the next boundary condition, but that will be in a next video because this can get longer. Thank you.